The next thing we want to do is find the area of a surface. And now we know how to express surfaces in terms of a parametrization, and that is what we're going to use. So let me remind you what we've seen in the previous episode. So given a surface, we can express it using a parametrization. We call the parameters u and v. So r of uv is a point in three-dimensional space, x, y, z, and each coordinate is a function of the two parameters. Okay? In analogy to the parametrization of a curve, which was r of t, x of t, y of t, z of t. The normal at every point for this parametrization was given by the cross product of the two tangent vectors. That's the normal at every point, and the two tangent vectors to the parametrization are r sub u and r sub v. So this is the normal. And now we want to find the area. The argument, the ideas behind this are going to seem similar to something we've already done, which is the Jacobian. And we'll see why it's similar. So here's the idea. We're starting with some domain in R2, This is D. And this is the UV plane of the parameters. And we're sending it, think pizza, to some surface. And the surface lives in the XYZ plane. Okay? So this is S. This is the surface. S is no longer flat, so finding its area is not something we can do by means of the regular ways of calculating area that we know. So we want to somehow find a method of finding the area of the surface S. How do we do it? So we're going to take a partition. So this is going to involve an integral, surprise, surprise. And we're going to take a partition of the domain here. So here's a partition of the domain here. And in order for our picture not to get too blurry, I'm just going to draw two segments of this partition. And we get here some little rectangle, which turned out to look like a square. Let's make sure it's a rectangle. There. Ah, terrible. Blah. Let's make it bigger. Okay. So this is V, this is U, this is our domain. The partition is into very small rectangles, but in order for us to be able to see, I'm drawing it big. I'm zooming in on one rectangle. Let's call this U. This is one of the UIs, and this is UI plus 1. I'm going to call UI plus 1 U plus delta U. And then this is going to be V, and this is going to be V plus delta V. Right? So remember, there's a bunch of these, and I'm just drawing one of them and intentionally making it very big so we can see what's going on. How is this picture going to transform when we send the dough up to the air? When we do this parametrization process, well, I'm going to get here some picture that looks like this. Right? That's what I'm going to get. And this original rectangle here is now going to be some shape up here. And it's no longer a rectangle. First of all, it's not flat. It's curved. Right? And moreover, the lines aren't parallel anymore. They're not necessarily even straight lines. Right? Because everything was distorted when we sent it up into the air. Do you agree? But the distortion, at least locally, when this is a very, very small rectangle, the distortion is not wild because of continuity. So if 2 points were nearby here, they would be nearby here. And therefore, if this was a line, so all the points are near to each other on this line, the distortion might make it into a little bended curve up here. And if these two lines are very close, if these two lines are very close, they're gonna be rather close here. Okay? So do you understand what I mean by saying that this is no longer a rectangle, it's no longer flat, it's no longer anything, but it's almost, when it's a small bit. Clear? So what we have up here, and we'll draw it now separately, so now I'm drawing only this thing. This thing is now some parallelogram that lives up here and looks something like this. Okay? Now let's identify these points on the parallelogram. So looking back at this board, this was u plus delta u, this was v plus delta v. So for example, this point here, uv, is going to be sent to this point here, which is r of uv, right? And maybe this point up here, which was u v plus delta v, is going to be sent to this point, which is now r of u v plus delta v. Okay? So I'm going to draw these points up here. This is going to be r of u v. That's this point. And remember that it's a vector. Okay? We can think of it. Here's the origin somewhere down here of our coordinate system. And we can think of this as a vector starting at the origin. This thing. This is r of uv, right? And up here, it's going to be r. Which one was which? I have to decide. That's r of u v plus delta v. That's the vector ending at this point. And this would correspond to r u plus delta u and v. Clear? And now we can find these vectors, the vectors that connect these points. So there's going to be a vector here, and I'm going to call it this vector here, I'm going to call delta r, or let's call it delta sub u of r. These are temporary names. So what is this thing? It's the difference between these two, right? So it's r of u plus delta u v minus r of uv. Do you agree? And likewise, there's going to be a vector here, which is the difference of these two, and we're going to call it delta sub v of r, because the difference is in the v coordinate, and this is going to be, so this thing is going to be delta sub v of r, which is r of u v plus delta v minus r of u v. And what's the area of this little piece of surface, this surface element, it's sometimes called? This little chunk of the surface, what's its area? Well, the area of a parallelogram, okay, these are arguments that should look very familiar if you remember what we did with interpreting the geometric meaning of the Jacobian. It's exactly the same ideas. So the area of the parallelogram is the length of the cross product of the two vectors which form its sides. Remember that? So the area of this surface element, that's what it's sometimes called, is the area of this surface element is the cross product, is approximately, because these are not exactly its sides, it's not exactly a parallelogram, so it's approximately delta u r cross delta v r. Do you agree so far? Everybody? Okay. And what is this? How can we calculate this? So it's, what I'm going to do, I'm going to divide by delta u and delta v and then multiply back. So I'm going to, so this is this, and then it equals, I'm going to rewrite it as delta u r divided by delta u cross delta v r divided by delta v. So these are scalars. So I put in these scalars here, but I can't just put them in. I have to multiply by them. So now I get this, right? And what is this? What's delta u r divided by delta u? This is delta u r, the difference of these two vectors. When I divide by delta u, what do I get? You're right, just say it out loud. You were talking about coffee this morning. So this divided by delta u, what does it remind you of? What does it look like? Right, it looks like the partial derivative with respect to u, right? What's missing is, well, first of all, it's the vector, right? So it's going to be the vector of the partial derivatives, x sub u, y sub u, v sub u. And what's also missing is the limit. In the definition of the derivative, there's the limit, and that's why this is not going to be equal, but only almost equal. That is almost equal to, and instead of this, I'm going to write r sub u cross r sub v delta u delta v. Do you agree? Everybody good? Okay. Okay. Now this was the area of this little surface element, this little piece of surface that we got, let's move one board back, that we got up here, which corresponded to this little rectangle down in the parameter space. Okay. Now if I want to know the entire area of the surface, I'm going to take the areas of all the little rectangles that I get here, okay, and sum them. Okay. So the area down here was delta u times delta v. The area up there was ru cross rv times delta u delta v. If I sum all of them, if I take the sum, I'm going to get the area of the entire surface. I'm going to sum the areas of all the little rectangles corresponding to all these little pieces in the partition. Okay. So back here, so this was the area of a single surface element, and therefore the area of S is approximately the sum over all the little rectangles of ru cross rv delta u delta v. This is a Riemann sum. I'm summing over all the little ui's and vj's. Remember, we denoted it u and v, but it was really a ui and a vj, right? We just didn't carry all these indices. And in the limit, when we take the partition, make it more and more refined, refine the partition, in the limit we're going to get that the area of S is the integral, the double integral, du dv of this thing, Now what is this thing? What is RU cross RV? One board back again. What is RU cross RV? The normal. So what we have here, the area of S, is taking the normal at every point, finding its length, and then doing a double integral over the domain. And note that all of this calculation is happening in the parameter space. Okay? Everything here is in U's and V's and D's, and everything is in the parameter space. In R2, that's why it's a double integral. And what we get is the area of the surface which we parametrized. Okay? So this can get a nice blue box. This is how we find the area of a surface. Good? Questions? Okay. So, good. Let's do some examples. Let's do some examples and some comments. So, first of all, I want to point out, how did we find the length of a curve? The length of a curve was an integral over the parameter t, so an integral from a to b, of the length of the tangent vector. Remember that? That was the length of a curve. Remember that? So now it's the double integral over the parameter domain, in this case a two-dimensional domain, not of the length of the tangent vector, but rather the length of the normal vector. Okay? That's one thing I wanted to point out. Let's do a simple example and then move on to more complicated things. So here's our first example, example 1. So I want to remind you that when we first discussed parametrizations, we found parametrization of a cone, where z ranges between 0 and 1, and the parametrization was r of uv equals u cosine v, u sine v, and u. This was a parametrization of this cone, and we found Ru and Rv. R sub u was, I mean, I'm actually copying this from my paper, but calculating it is just as easy and as quick. So I'm going to write it, and you're going to verify that I'm doing the right thing. So this is Ru. Rv is minus u sine v, u cosine v, and 0. And therefore the normal, which is Ru cross Rv, and it's this determinant I, j, k, and then these. So we have cosine v sine v1 minus u sine v, u cosine v, and 0. And what we got here was minus u cosine v minus u sine v and u. Okay, so this all of this we already did. So take a quick look and tell me if you agree. Now we want to find the area of this cone, right? We're taking a piece of paper, we're rolling it, and we're getting this cone. Do you know what shape you need to take in order for it to become a cone and not to have these weird things? Figure it out. That's an exercise. I'm not sure this corresponds to this parametrization. In fact, I think it doesn't. But anyway, so this is the normal. What do we need in order to find the area of the surface? We need the length of the normal, right? So what's the length of the normal? The length of the normal is the length of this vector. So it's the root of the squares of these. So I get u squared cosine squared v, plus u squared sine squared v, plus u squared, and all of this I have to take a root. That's the length of the vector. So here I get u squared cosine plus u squared sine squared, so these two give 1, so I get u squared plus another u squared, that's 2u squared, and then I take the root, so I get root 2 times u. That's the length of the normal vector. So what's the area? So area of the cone, it's the surface area, just the area of this surface, without the top. The surface itself is just the cone itself. So the area of the cone is the double integral over the domain of the parameters. So the domain of the parameters was u ranged between 1 and 0, and v ranged between 2 pi and 0. That was the domain of the parameters. So I have the integral between 0 and 1 du, and the integral between 0 and 2 pi dv, and all I have to put here is the length of the normal, root 2 times u. That's what I have to calculate. Do you agree? Okay. I already wrote it as an iterated integral. I did the step of writing it as an iterated integral. What do I get? So the integral dv, this doesn't depend on v, just introduces a v between 2 pi and 0, so I just get 2 pi, and this root 2 can also hop out, so I get 2 pi times root 2, and all I'm left is the integral from 0 to 1 of u du, which is u squared divided by, let's write that, 2 pi root 2 u squared divided by 2, evaluated between 0 and 1, and that gives us a half, cancels out with this 2, so I just get pi times root 2. A product of two of my favorite irrational numbers. Okay, questions about this? Very easy example. Is it clear? Everybody good? Okay. So that's example. That's the first example. The second example I want to do, let's find the surface area of a sphere. Okay, so we have a sphere. We want to find the area of the surface. Okay, not the volume, the area of the surface of the sphere. So this requires a bit more calculation, so I prepared it in advance so we don't waste time on writing it and me making a lot of typos and so on. But let's just read it out. You can always press pause and do it slowly. So this is a sphere of radius r, centered at the origin. Looks like that. So here's a sphere centered at the origin. Okay, I want to find the surface area. R is the radius. It's a fixed number now. Okay, so I'm only looking at the points on the sphere, points which satisfy that the sum of the squares of their coordinates equals r squared. Okay, and I want to find what is the surface area. So let's find the surface area. Small s. So that's what we're going to do. So the first thing we have to do is parameterize the sphere. And the parametrization stems from spherical coordinates, but this is not changing variables. It's not spherical coordinates for the entire xyz space. That's not what it is. It's only the points on this sphere. So r is fixed. It's this fixed r. Okay? And the only two parameters that vary are theta and phi. And since we want all the points on this sphere, theta goes the entire range from 0 to 2 pi, and phi goes the entire range from 0 to pi. Do you understand why I'm doing this and this? Okay, remember how we defined the spherical coordinates. Okay, so this points of this form, x, y, z, defined like this, where this is the range of theta and phi, give me only those points sitting on that sphere of radius r. Does everybody agree? Does everybody see that? Clear? So this is the parametrization of this sphere of radius r. Okay. Now we want to go through the process of finding, let's look back one board, finding the area of the sphere. The double integral over the domain of the parameters of the length of the normal vector. Okay, so let's do that. So here's our parametrization again. I have to calculate the normal. The normal is the cross product of r theta cross r phi. R theta cross r phi. This is the order I chose because I wrote it r of theta and phi. You can reverse the order. Okay, you'd get the normal in the other direction, but eventually you're going to calculate its length, so it doesn't matter. Okay, so I just wrote the derivatives of each coordinate of x, y, and z. So this is x sub theta, y sub theta, and z sub theta. This is z sub theta is 0. I just explained the easiest one. Clear? Everybody with me? And these are the coordinates. These are the components of r phi. Okay, the derivative of x with respect to phi. So it's r cosine theta cosine phi. There it is. And so on. Okay. And now I'm calculating the determinant. And you can check. Everything is going to have an r squared and in fact a minus, so I pulled out the minus out here, and this is what I get. This is the vector. This is the normal vector at every point. Okay? And the length of the normal vector is just squaring all these components and taking the root, and things cancel out nicely, and this is what I get. R squared sine phi. Questions so far? Okay? So I found the length of the normal vector, no snakes so far. Now what I need to do in order to find the area is take the double integral over this domain of this. Cool? So let's do that. Let's do it maybe, let's devote some new space for that. So let's do it here. I don't know if you noticed, we got a nice new yellow eraser. That's soft. Very nice. This happens very rarely here, so it's exciting. Okay, let's leave this. And it's not going to be yellow soon. It's going to be black. Okay, so the area of the sphere is the double integral over the domain. Let's write it as an iterated integral right away. So from 0 to 2 pi d theta of the integral from 0 to pi d phi. And now I need to plug in here the length of the normal vector, which we calculated, r squared sine phi. Good? And let's see what we get. So remember that r is fixed. It's the radius of that particular sphere. So r squared is not a variable. It can hop out of the integral. And we get the integral from 0 to pi of sine phi. So let's write it. The integral from 0 to 2 pi d theta. And now the integral of sine phi, so it's minus cosine phi, evaluated between 0 and pi. So we get r squared times the integral from 0 to 2 pi. And here we get cosine at pi cosine, look what I'm doing with my hands, tell me if you agree. Cosine at pi is -1. And there's a minus here, so it becomes 1. And then there's minus because of the lower bound, minus because of this, so it's a plus. Cosine at 0, which is also 1. So I get a 2 here, and here's our d theta. The 2 hops out, and the integral from 0 to 2 pi d theta is just 2 pi. So I get, what? 4 pi r squared. Good? Did you know that that's the surface area of a sphere? Well, now you do if you didn't. And it compiles, at least in terms of being of power 2 with respect to the radius. Okay, it sounds area-ish. If we would have gotten a cubed here, it would be volume-ish. Something would be wrong. Do you agree? Okay. Okay, so that's the surface area of a sphere. That's our second example. I want to do a couple of calculations, which are not really examples, they're sort of remarks. So I'll erase here. And here are some remarks. So remarks. Number 1. Suppose you're taking a surface which is flat. You want to calculate the area of a surface, but that surface happens to be a flat surface. It can live on the xy plane. It could live up here, okay? But it's still flat. It's a planar surface. So imagine doing this with a pizza, but only spreading it, but still keeping it on one flat surface. Okay, so I don't know how you can actually do that. It would automatically look like this, but suppose you can do it. Okay, we need to practice. We need to practice our pizza skills. That's obvious. So what would the parametrization? So if S is a planar surface. So it's some domain in some plane. Okay. What would the parametrization look like? So the parametrization R of uv is going to be of the form x of uv, y of uv, and z of uv, but z of uv is going to be fixed. Okay, it lives on some plane, let's say. Z is some constant. Of course, it can be a planar surface living like this, or like this, or like that, but just for simplicity, let's assume it's living on a plane up here, somewhere, on some constant Z. Okay? It's not the entire plane, it's some domain in that plane. What is, so obviously for this we get, so ZU, Z sub U, as well as Z sub V are both 0, right? Because Z is some constant. And therefore, hence, what do we get when we calculate the normal? Remember, the normal had those components ijk, and then xu, yu, zu, xv, yv, zv, right? But both zu and zv are 0, so the only thing that remains from the normal is the k component, and that little minor, the little determinant of, tell me if you agree, xu, yu, xv, yv. Do you agree that that's the normal? Do you see the imaginary things I did here? Okay, the original normal had I, j, k, and then 2 zeros here. So this is the only component that remains. Everybody with me? Okay. So what is the length of the normal? So the length of the normal is the length of this vector. Okay, this is a vector with only one component, right? So I have to square the component. 0 is the I component squared, plus 0, the j component squared, plus this squared, square root. So it's the absolute value of this coefficient, of this k component. Okay, so it's in fact the absolute value of this little determinant. And what is that little determinant? Do you recognize it? It has a name. Right? It's precisely the Jacobian. Do you agree? Okay. So what just happened here? And this implies that the area of the surface is the double integral du dv of the Jacobian over the domain. So what just happened here? What happened here is taking a planar surface, parametrizing it, taking parameters from another surface, another flat surface, is really just changing variables. Going from uv in the uv plane, where the parameters lived, to xy in the some other plane. Do you see that? So this coincides with changing variables, and we know that calculating an area, okay, calculating the double integral of the area would just introduce the Jacobian, right? It's like changing variables. So in this case, this coincides. It's really nothing else. Changing variables. This is simply changing variables. Okay? So when you do this process, but just do it in a planar way, all you're really doing is changing variables. Okay? And that's why the calculation of this, of the area, was very similar to the way we calculated and interpreted geometrically the Jacobian. It was really the same idea, except that now it's more general because it's not just doing it in the plane, but rather doing it in general in three-dimensional space. Is this clear? Okay, I'm not going through all the details, but is it clear? Okay. A couple more comments. So the only other two comments that I want to make is what happens. Remember that we're starting with a parametrized surface. That's how we got all this analysis and eventually the formula for the area. What happens if you start with a surface that's the graph of a function, right? That's a very simple case. So remark number 2, if S is the graph of a function, okay, so it's all the points x, y, z satisfying that the z is f of x, y, then there's a very straightforward, simple, obvious way of parametrizing it. How would we parametrize it? Then we can write, instead of parametrizing it with u and v, let's just parameterize it with x and y. So r of x and y, the x is just going to be x, the y is just going to be y, and the z is going to be fxy. Do you agree? In analogy to parametrizing a curve, when the curve is the graph of a function, when the curve is of the form y equals f of x, for example, then the parametrization is x comma f of x, right? So this is a parametrization of a surface which is the graph of a function f of xy, right? what would be the normal in this case? So n is going to be I, j, k. And now I need the components of x with respect. Let's write it here. N is x, r sub u cross r sub, no, I'll get it eventually. R sub x cross r sub y. These are the two parameters. So what's Rx? It's the derivative of the first component with respect to x, 1. The derivative of the second component with respect to x, 0. The derivative of the third component with respect to x, which is what? Right. Now I need the derivative with respect to the second parameter. So x with respect to x is 0, y with respect to x is 1, and z with respect to x is f sub y. Do you agree? And therefore, what is this vector? In the I component, I get minus fx. In the j component, I get fy with a minus because of the j. And in the k component, I get 1. This is the normal vector, right? We knew that. Do you remember when we saw this? I'll remind you in a second. We knew this. Okay, but let's just see what the length of the normal is. So the length of the normal is the root of the squares of these components. I want to write the 1 first. So it's 1 plus fx squared plus fy squared. And therefore, the area of the surface, which is the graph of a function, is the double integral dx dy this time of the root of 1 plus fx squared plus fy squared root. Okay? Very similar to the length of a curve, which is the graph of a function, where there was no fy squared. It was just, let's add these parentheses here. Good? I want to remind you where we saw this. This is a surface, and what we found is the normal vector to the surface. Surface, normal vector to the surface. Remember a statement that we had, that if we have, how did we phrase it? We said the gradient is always perpendicular to level surfaces. Remember that statement? Does everybody remember that statement? And the way we proved it was via the implicit function theorem. It was a pretty long discussion. It took us some time to derive that, but eventually we got to the conclusion that just like the gradient is perpendicular to level curves for 2 dimensions, the gradient is perpendicular to level surfaces for 3 dimensions. Remember that statement, everybody? Okay. So if we have, I want to remind you of this because it's illuminating. I think it's important. So I want to show you that if we have z equals f of xy, if we have a graph of a function, the normal is indeed this. Okay, so why is that true? So here we did it by means of parametrizing and finding the normal the way we just learned, but I want to show you how we did it previously. And in fact, my last remark is going to be how we find the area of a surface which is given by an implicit function. Okay, so let's add a box here so you can highlight this in your notebooks. This is again a formula that you can use, or you can derive it from scratch. It's not very hard. But I want to show you why this is true. So if we have z equals f of x, y, this is a level surface corresponding to c equals 0, so the 0 level surface of the function f of x, y, z equals z minus f of x, y. So if somebody gives you this surface, it's the graph of a function, define a function of 3 variables, capital F of x, y, z, to be z minus f of x, y. All the points x, y, z where capital F is 0, that's the 0 level surface of this function, are precisely the points where z equals f of x, y. Do you agree? Does everybody see, does everybody understand these two lines? That's the crucial step here. Okay, so when I have a graph of a function, it's precisely the 0 level surface of a function of 3 variables defined like this. Do you see that? Good? Everybody? Okay. What's the gradient? The gradient of f is what? Is the vector of the partial derivatives with respect to each coordinate. So let's write it. It's f sub x, f sub y, f sub z. That's the gradient by definition, right? What is it? What's the derivative of f with respect to x? It's just minus f sub x. Do you agree? What's the derivative of f with respect to y? It's minus f sub y. And what's the derivative of f with respect to z? 1. Do you agree? And the statement that we had, which we proved carefully using the implicit function theorem, was that the gradient is perpendicular to level surfaces. This is a level surface, and the gradient is perpendicular to it. So this is the normal. Clear? And this is precisely what we found before. Okay. Therefore, minus fx minus fy 1 is the normal to the surface. This is a bit loose. This is loosely speaking, okay? Because it's actually the normal to the tangent plane to the surface at the point. But I'm just saying the normal to the surface. To the surface, z equals f of xy. Clear? Okay. So one final comment. Is this clear? Did everybody follow this? Okay. So one final comment. So this is the area of a surface for a general parametrization, R of uv. This is the area of a surface for a specific parametrization, which we can only write in the situation where the surface is the graph of a function. And the last thing I want to write is what is the area if the surface is given by an implicit function. F of x, y, z equals 0. Okay, so let's write that. So this was remark number 3. If S is some implicit function, a surface given by some equation, okay, an implicit function, then by the implicit function theorem, implicit function theorem, we know that there is, at least locally, we can express z as f of xy. I'm assuming that everything is smooth, everything is C1, everything works. So we can write z as f of xy, and we know the derivatives. And fx is minus fx divided by fz, and fy is minus fy divided by fz. Okay, make sure that when you're writing things like this, there's a clear distinction between your lowercase f's and your capital F's. Okay? Remember these things? Everybody find them familiar? Okay. Therefore, the normal is going to be, what's going to be the normal at every point? So I'm still going to parameterize it as if it were the graph of a function, because I know that implicitly it is the graph of a function. I can write z as a function of x and y. I just don't have a formula for it. But I don't need the formula for it. I only need the normal, right? So what is the normal going to be? The normal is going to be minus f sub x, right? Let's look back at this board. This is the normal, right? I want to write it. Minus f sub x, minus f sub y, and 1. It's still given by the graph of a function, except that now this is implicit. I don't know the formula for this. But I don't need the formula for this. I only need the derivatives, and the derivatives I know by the implicit function theorem. Clear? So the normal is minus f sub x, so it's minus minus, so it's just fx divided by fz. And these I know how to find. This is given. Okay, these are the partial derivatives of the function f. F is given, right? And then the y-coordinate is minus this, so it's fy divided by fz, and 1. That's the normal, right? And therefore the length of the normal is the root of the sum of these. So I'm going to divide by f sub z. So it's fx squared plus fy squared, plus, I'm going to write this as fz divided by fz. Okay, let's rewrite it. Let's rewrite it even before we do this. I'm taking a step back. I'm going to write this as 1 over f sub z times fx, fy, fz. Let's rewrite it like that. That will be easier. Do you agree? Okay. And now the normal is the length of this thing. So this is a scalar. I just need to square it and take the root, so it gets absolute valued. And then the root of the squares. This is the length of the normal, and therefore the area of the surface given by an implicit function is the double integral dx dy of, what's this? Can you give me a shorter way of expressing that? Down here there's going to be the length of fz, but what's this? Look, it's the square, it's the root of a sum of squares, so it's obviously the length of a vector. What's the vector? It was this vector, right? What is this vector? A vector whose components are the partial derivatives of f. Exactly. So I can write this in short, the gradient of f. Good? So you can put another final box around this. And this is really all I wanted to say about finding areas. Quick summary. This was a rather long clip. Quick summary. The area in general, you find a parametrization. U and V are the parameters. You have R of UV. For R of UV, you can find R sub U and R sub V. Take their cross product, you get the normal. Find the length of the normal, then you can calculate the area of a surface. Okay? If the surface is given by a function, the graph of a function of two variables, then the area is this. Okay? If the surface is given by an implicit function, then the area is this. Okay? Very straightforward calculations. Everything we did in this clip was not too complicated. And now all you need to do is do some more examples on your own in practice. We're going to do more examples together as well, but what I do want to add is not just the, so that's where we're heading. For curves, we started out by parametrizing curves. Good, we parameterized surfaces. Then we found the tangent vectors. Good, now we have the normal vectors. Then we found lengths of curves. Now we have areas of surfaces. And the next step was to throw in some functions. So instead of just the length of a curve, we had the integral over a scalar function over a curve, right? We want to do that for surfaces. And then we had the integral over vector fields for curves. We want to do that for surfaces. Okay, so the next step is what are called surface integrals for scalar functions and for vector fields. Coming up next.